Hello everyone, welcome. In today's video, we'll delve into the four essential steps of the C compilation process. As a continuation to our previous video where we mentioned that the C compilation process is basically divided into four phases, namely pre-processing, compilation, assembly, and linking. In today's video, we'll see with an explained example how these four steps look like in this C compilation pipeline. So the first phase, as you guys remember, is the pre-processing phase. So before going into pre-processing phase, let us look at this source code example, which we are going to use throughout our video. Here we have a simple hash include directive for standard IO, as we are going to use the printf function, and we also have a macro call message with the simple hello world string, and inside the main function we are simply printing this formatted string hello world, and then we are returning. So this is a very bare minimum C process. Now let us look at how pre-processing phase will look like on this thing. So as we know, C source files contains macros, as I have already shown, that is hash defined, and hash include directives with .h extension. So the pre-processing phase basically expands any hash define and hash include directive in the source file so that all that left it's pure C code ready to be compiled. Let's make this more concrete by looking at this particular example. By the way, in this video, I'll be using GCC compiler, which is the default on many Linux distribution. Anyhow, the results on other compilers like Clang or Visual Studio would be similar. And I'll also be using this x86-64 code and not ARM or anything else. So now, in a moment, now you'll see what happens with this file, that is a C compilation.c source file I have shown you in the rest of the compilation process. But for now, we'll just consider the output of the pre-processing state. So by default, GCC will automatically execute all compilation phases. So you have to explicitly tell it to stop after pre-processing and show the intermediate output. So for GCC, this can be done by calling simply GCC minus E and minus P followed by the C file. So minus E tells GCC to stop after pre-processing, and minus P causes the compiler to omit debugging information so that output is a bit cleaner. So once you do that, you have the expanded code after the pre-processing phase. So if you see, there are so many things like type defs followed by multiple structure for IO file, then another structure, then a few bunch of externs, that is the global variables, and the rest of the main function you can also see. So the stdio.h header is included in its entirely with all of its type definitions, global variables, and function prototypes copied into the source file. Because this happens for every hash include directory, preprocessor output can be quite verbose. The preprocessor also fully expands all of the use of the macro. If you remember the C code, here we had one macro message which was called in the printf function. But when you look at the preprocessed output, you see the printf is already replaced with the macro that is hello world. So this is pre-processing step. Now we'll go to the next step, that is the compilation phase. After the pre-processing phase is complete, the source is basically ready to be compiled. The compilation phase takes the pre-processed code and translates it into assembly language. So the output of the compilation phase is in assembly in reasonably human readable form with all the symbolic information intact. As mentioned, GCC normally calls all compilation phases automatically, so you have to explicitly tell it that give me the assembly code, and this can be done using GCC minus S flag. So to all the guys. So this s.s extension is basically used for assembly in extension, so that is why minus s. Apart from that, we'll also give ASM, that is emit the assembly instruction in Intel format. So there are a bunch of formats like Intel AT&T syntaxes, but for now I'm using Intel machines and I will focus on this NT, followed by your C file. So once it is done, your assembly output will be shown in this same name but dot s instead of dot c. So this is the assembly information you can see, and you can also see this bunch of symbolic information are still mentioned. That is, this is where the main function starting, and there is another symbolic variable called .lc0, which is basically pointing towards this hello world string, and somewhere down the code it will reference to that location so that it can load the hello world string in the memory and it can print it in the stdio. So this is the assembly code. As you can see, this is quite human readable, and this is still compilation phase. So once the compilation phase is done, we move to the assembly phase, and in the assembly phase you finally get to generate some real machine code. The input of the assembly phase is a set of assembly language files generated in the compilation phase, and the output is a set of object files, sometimes also referred to as modules. So to generate the object file, you just simply do gcc minus c, and then you give your .c file. So when you run this, there one object file is created, which is basically with the same name but .o instead of .c. And this file is basically a Linux utility, which is helpful to know the properties of this module. um, there is some quite interesting things comes up when you do this file c compilation.o. Four important things to note: that it's an ELF file, and I'll mention what ELF is, and it's a 64-bit, and LSB, I'll also mention what LSB is, and this is also relocatable. So let us look what does it mean by this ELF 64-bit LSB relocatable file. The first part of the file output shows that file conforms to the ELF specification of binary executable, which is basically executable format for Ubuntu systems. And more specifically, it's a 64-bit ELF file. As I have already mentioned that we are compiling a x86 64 file in this example. It is LSB, meaning that numbered are ordered in memory with the least significant byte first. But most importantly, you can see here the file is a relocatable file. So relocatable file don't rely on being placed at any particular address in memory. Rather, they can be moved around at will without this breaking any assumption in the code. So object files are compiled independently for each other. So for each C file, there will be one object file. But later on, we might have to merge those object file and create a single coherent binary executable. If these object files are not relocatable, this will not be possible because they don't know from which location the other object files are being accessed, right? So once this is done, we move for our final phase, that is the linking phase. So the linking phase is after this assembly phase. As the name implies, this phase links together all the object files belonging to a program into a single binary executable. And the program that performs the linking phase is called a linker or a link editor. So most compilers, including GCC, automatically call the linker at the end of the compilation process. So if you do GCC minus O, and let us give our name to this binary executable, let's call C example, and then you give the C file. So once you do that, all the processes, that is pre-processing, compile and assembly, will be done, and the linker will also be called directly. And now you will have a binary called C example. So this -o flag is used to rename the whatever binary executable is creating by GCC. So if I run this example, you can easily see that hello world is coming up. But what we are more interested in is looking at the properties of this binary executable. Yay, so many interesting thing to note. So by default, the executable name is a.out, but we change the file name by giving this -o flag, which will override the a.out and it will give your desirable names. So once you call this file utility, there are so many interesting things. First of all, it's an ELF. I have already mentioned it's a particular binary executable format for Linux machines, and it is x86 64-bit, and it is still following this LSB executable rather than um, LSB executable. And one more thing, other important information is that here file is dynamically linked. Here, if you see, the file is dynamically linked, meaning that it uses some libraries that are not merged into the executable but are instead shared among all programs running on the system. And finally, the interpreter, if you see, this is the interpreter, um, i- which will which dynamic it will tell you basically which dynamic linker will be used to resolve the final dependencies on dynamic libraries when the executable is loaded into the memory to be executed. And one important thing, if you notice, this earlier this relocatable term was there, but now here if you see, this is not relocatable anymore, because all the object files has been merged to this one particular binary executable called C example. And another thing which you can notice is there is a thing called not stripped. So this is another domain, and maybe I'll discuss what this means in a binary executable in the next video. Stay tuned. So to sum up, we have covered the 4 steps of C compilation process: pre-processing, compilation, assembly, and linking. Our example of the Hello World program allowed us to see the transformation of code from source to executable. Understanding this process was fundamental for any C programmer. So I thought maybe creating this video help you guys. Um, Lastly, thank you for joining me in this video. If you find it helping, don't forget to like, subscribe, and leave your comment below. Stay tuned for more exciting content, and happy coding.